Welcome to the CompTIA A+ 220-1101 or Core 1 exam, Objective 2.5, Assigning IP Addresses. In a previous video, we talked about a manual configure of IP address that includes an IP address, a subnet mask, a default gateway, and a DNS setting. Of course, there are other IP configuration settings as well. You can imagine an enterprise network where you have hundreds or even thousands of devices. Manually configuring IP addresses is not going to scale very well. And that's why in October of 1993, we created a protocol that can automatically assign IP addresses to devices. We refer to this as Bootstrap Protocol or BootP. BootP was a good start, but it didn't assign all of the different configuration settings that we needed. There were still some manual configurations that you had to do yourself, and BootP had no idea when a device would leave the network, so that it could use the IP address for another device later on. To correct some of these shortcomings, we created new versions of BootP, and we gave it a new name, the Dynamic Host Configuration Protocol, or DHCP. DHCP has been around for quite some time, since 1997. And it provides an automatic configuration of IP addresses, subnet masks, default gateways, and many more settings as well. We often don't think about the process DHCP goes through to assign these values to your computer. We simply turn on our system and magically we have an IP address. But behind the scenes, there are a series of steps that take place to provide that IP configuration to your device. We refer to these 4 steps as DORA. The first of these is D step, or discover, where our devices will try to locate a DHCP server that's on our local network. The next step of O is to offer, where a DHCP server will offer an IP address to our device. Our device will then look at one of the many offers that we receive, pick one of those offers, and then request the IP address from the offering DHCP server. And finally, that DHCP server will acknowledge that offer and provide your system with all the IP configuration settings that it needs. You can look at these steps below to see exactly how the process works. The step 1 of DHCP process, or the discover part of the process, has a workstation sending a broadcast out using UDP port 67. This broadcast will be sent to all devices on the local network. And all that broadcast is going to be sent to both the router on my network and the DHCP on the network. One of the things that you'll probably remember from looking at broadcast, multicast, and unicast is that routers will not allow broadcast to pass. But you'll notice in our example that the broadcast did pass through the router and was directed to a DHCP server. That's because we've effectively configured the router as a DHCP proxy. Sometimes you'll see this referred to as a DHCP relay. Now that the 2 DHCP servers have received the request, we can move to this next step, step 2, or the offer phase. These 2 devices will send their offers back to the original client workstation. This is often sent to broadcast address over UDP 68. The reason why we're using so many broadcasts is because, remember, our client workstation does not have an IP address yet. Now that is the message is sent to the client workstation. It can examine both of these offers and make a decision on which offer it should take for the IP address assignment. The client workstation will send another broadcast over UDP port 67 on step 3, or the request phase. This broadcast contains a formal request to take the offer that was originally sent. And in this particular example, I'm only showing communication that's occurring between the client workstation and the DHCP server that made the original offer. But of course, since it's a broadcast, it should go to every device on that network. This 4-step DORA process happens every time a device connects to the network and needs to obtain an IP address from a DHCP server. When these DHCP servers were first configured, a range of IP addresses was configured inside of that server to hand out the different clients. We refer to this as a pool of IP addresses, and the IP address that you may pull one day from this pool may be different than when you might use on a different day, but there might be some devices on your network that would prefer always receive exactly the same IP address every time it starts up. There might be a printer, a server, or some type of infrastructure device that you would prefer to always have the same IP. One of the ways that you could do this is simply disable DHCP on all of those devices and manually configure them yourself. This obviously requires that you administratively make these changes, and it could take quite a bit of time to do all this on a network. You would have to revisit these devices if you ever wanted to make a change again, and it's quite messy. In a very large environment, that might not be practical at all, and it certainly requires additional administration. Instead of manually setting an IP address, we can configure a reservation on the DHCP server itself. This means we'll configure a specific MAC address of a printer, a server, or another device on the network and tell the DHCP server that every time you see this MAC address, it should provide a reserved IP address. This way, when we start up the printer or the server, it's good to go and it will work as soon as it turns on. The problem is that when there are changes to the network, you have to go back every single one of these devices and make a change on the console, and it can reflect on the entire network. Like most things, there is a standard for automatic private IP addressing. This is the entire range from 169.254.0.0 to 169.254.255.255. This particular standard reserves the first and last 256 addresses. So if you're assigned an APIPA address, it will be a random assignment between those IPs. If you see any of those IP addresses on a system, then you can automatically assume that a DHCP server was not available when the system started up, and you will only be able to communicate with other devices on your local network. Like DHCP, APIPA addresses are also assigned automatically, but the only device determining what IP address you receive is the local device itself. Okay, we're at the end of 2.5, assigning IP addresses. Here's a pretty common question I see on the A+. Which of the following is an APIPA address? Is it A, a 192, B, a 172, C, a 169, or D, an 8 address? And the answer is C, it's 169.254, and then anything after that is acceptable and will be an APIPA address. Thanks for watching.